The idea for this video came from Carrie. I hope you find it helps you too. We're going to have a look at how some equations in physics link together, and I'm focusing on the equations from forces and energy. Here is a book. It's on the floor, so let's talk forces first. The book has a mass, which is measured in kilograms because it's made from matter. But here on Earth, gravity pulls down on masses by 10 newtons on every kilogram. So the book also has a force called weight, which is acting downwards. The floor is pushing back up with an equal sized force in the opposite direction, so everything is balanced. The weight in newtons can be calculated using the equation weight is mass times gravity. We just multiply the mass by the gravitational field strength of 10 newtons per kilogram when we're on Earth. There's no resultant force here, and so if we think about the F equals ma equation, we've got no acceleration yet. It's just stationary on the floor. But I'm going to come back to F equals ma soon. I can do work on this book. Work against gravity if I lift it up. So if I was to put this book up on a shelf, work would be done and measured in joules. As the force, the weight of the book in newtons, moves through that vertical distance, the height in metres, the work done is equal to the force times the distance moved in the direction of the force. Work done is another name for the energy transferred, and that's why they're both measured in joules. By lifting the book up onto the shelf, I need to transfer energy to it to get that work done. Up on the shelf, the book stores gravitational potential energy, also in joules again. Gravitational potential energy can be calculated using the equation mass times gravity times height. And here's our first link. If weight is mass times gravity, and work done is force times distance, then gravitational potential energy is linked because the weight in newtons is being multiplied by the height or distance in metres. Okay, so now we have a book on a shelf. The forces are balanced again. There's no resultant force. But say it falls. If the book falls, there's a resultant force. I said I'd come back to F equals ma. The resultant force here is from the weight of the book, the weight in newtons. And that's equal to the mass in kilograms times the acceleration because of gravity pulling the book down as it falls from the shelf. And that gravity is pulling at a rate of 10 metres per second squared, the acceleration due to gravity. In real life, the air resistance will provide an opposing force, and as the air particles hit the falling book, they'll push upwards, reducing the resultant force down a little bit, but not enough for me to allow for it here in these calculations. I'm assuming no air resistance now to keep the equations simpler for you. So, weight is mass times gravity, and it links to resultant force is mass times acceleration, because resultant force is weight in newtons on this mass in kilograms, and the book accelerates downwards as it falls at a rate of 10 metres per second squared because of the gravitational field strength on Earth. As the book falls, the gravitational potential energy decreases because the height is less and less. And of course, gravitational potential energy is mass times gravity times height. As the book falls, the kinetic energy increases because the book is falling faster and faster as it falls. It's accelerating. And it's accelerating in the same direction. Its velocity is increasing because it's getting faster. Kinetic energy can be calculated from the half mv squared equation. Now we know from the law of conservation of energy that energy cannot be created or destroyed. It can only be transferred. And so, if we're assuming no losses because there's no air resistance in our problem causing energy to get wasted as thermal energy as the air particles collide with the book, we can say in our example, all of the gravitational potential energy will eventually all become kinetic energy. The total gravitational potential energy is equal to the total kinetic energy. So combining the two equations, mgh must therefore be equal to a half mv squared. Do you see the mass just cancels out? It's on both sides of the equation. So gh is equal to a half v squared. Now that means if I double both sides of the equation to keep things balanced, 2gh is equal to v squared. And so v can be found, the velocity the book hits the ground at, and it would be calculated by finding the square root of 2 times g times h. As the book falls, energy is transferred. The time it takes for the book to fall, the time it takes to transfer all the gravitational potential energy into kinetic energy, allows us to calculate one last thing: power. Power is the rate of transferring energy. It's how quickly energy gets transferred. Power is therefore energy divided by time. The energy transferred divided by the time it takes to transfer it. And that, of course, is the same as saying that power is the work done divided by time. 1 watt is equivalent to 1 joule per second. So when I lift the book from the floor to the shelf, I always transfer the same amount of energy. It's the same force, the weight of the book, through the same distance, the height of the shelf. But the quicker I do it, the more powerful I am. It really is quite beautiful, the way the maths of physics all comes together and connects. All of these equations we've connected in this short video. Good luck to all my Year 11s who are doing P2 this week. I hope you get the paper that allows you to show that.
Regular review gets a better grade for you.
Don't forget to
Like,
so that I can keep making the videos.
comment,
Especially to request other revision topics.
subscribe.
So you can get notifications of when my next video gets uploaded.